Hi everyone and welcome to this video. So last time we focused on the Atari 800, on the emulators that are available, and we also focused on a little bit on the Atari DOS and on the Atari Turbo Basic. This time we are going to use these tools and we are going to continue to see how we can use the Atari to achieve very interesting things. In particular, I'm going to focus on one demo, which is a demo that I presented on this channel a while ago. So you can find it on this link here. I will report this link in the description below. And what we are going to do is to describe the demo and to provide a few details on how I did achieve what you can see there. Eventually, once this is explained, I'm going to introduce the main concept that I have exploited in order to create this sort of computation. And in particular, we are going to introduce artificial neurons, but also artificial neural networks, which is an important concept in the field of machine learning. And we are going to spend a few words on how you can train those neural networks before you can use them. Eventually, we are going to see how to obtain an artificial neural network inference in BASIC on the Atari. And all of this will be done through the use of examples. As usual, I'm reporting a few useful links here. They will be reported in the description below, of course. The first link, so in case you don't have access to an Atari 800, this link can be very useful because you can download an emulator of the Atari. So if you haven't done that, I warmly suggest you to download and to install Altera. On this link here, you will find a few guidelines on how to find Atari DOS and how to find Turbo Basic. And in these two links here, practically you will find instructions on how you can train your neural networks. Of course, I'm going to explain all of this. There is also a book that I always suggest when we talk about machine learning. And this is a book from Bishop. The title is Neural Networks for Pattern Recognition. This is a book from 1995, so it's a relatively old book, but the main mathematical tenets of the whole discipline are there, and this is a very simple book to understand. So I highly suggest it to whoever wants to understand machine learning and wants to have a very good foundation in machine learning. As usual, I want to take advantage of this video to thank all of you. I know that I repeat this very often, but this is very encouraging, seeing that you guys are subscribing to this channel, or you are leaving comments, you are putting likes. This is very encouraging. This is pushing me to provide more videos. So thank you to all of you for doing this. So what is this demo about? When I refer to the demo, I'm actually referring to this video here that you see in this link here. And I'm going to show an extract of the demo that you can see now on the screen. And this demo essentially shows a neural network that has been trained, and that has been trained in a certain way, and then the network has been migrated and implemented in BASIC on the Atari 800. So what you see here, it's a network that has been trained to recognize handwritten digits. And the way we have done this was to use a trainer or let's say a training method for the neural network, and a data set which consists in this particular case of the MNIST data set, which is essentially a set of 60,000 handwritten digits that have been collected so that you can train your neural network. So what you see here every time is a neural network that is capable of recognizing handwritten digits, which is practically not that trivial, especially if you want to implement this by hand. In practice, the only way you can achieve this sort of computation is through the use of artificial neural networks. So practically, this is where we are going to focus now. Of course, before we can talk about neural networks, we have to discuss a little bit about artificial neurons and what they are and how we can use them. So in practice, an artificial neuron is something that is inspired by biological neurons. And you can think of a biological neuron as essentially a cell that take an input in the shape of some current and provides an output in the shape of a current again. The current usually has the shape of spikes. So you have trains of spikes as input and you have trains of spikes as output. But all of these is simplified and abstracted on a computer. So rather than having a certain number of spikes or a train of spikes, we just count the number of spikes per unit of time. And this is what we are going to use as input and output of these artificial neurons. So all of a sudden, because we are introducing now this abstraction, you can think of an artificial neuron as a function that takes several inputs. So in this particular case, you can see we have x1, x2, xn, and so on. It's going to provide some processing on this input, and it's going to provide the value y that you see as the output in this figure here. Of course, an artificial neuron doesn't come alone. You want to connect those neurons with each other, more or less like it happens with biological neurons. Biological neurons are connected with each other, and this is how they can practically achieve all the wonderful things that we see in nature. So in the same way, we want to have these artificial neurons being connected with each other. So it means that essentially the output of one artificial neuron can become the input of another artificial neuron, and these neurons are now connected. So we can now introduce the concept of weights, where a weight become, let's say, a number that describe how much connection there is between two neurons. What do we need? What do we mean by that? So you might have two neurons that are connected. So the output of one neuron becomes the input of another neuron. But this connection can be very, very strong or very, very weak. So you need one number that is going to express this weakness, or let's say the strength of connection between the two neurons. So the way we do this is through a number. We call this number a weight. So in this particular figure now, what you see is that if you have input x1 that is coming from a neuron, this input now has a weight that is assigned to it, and you are going to use this weight to describe how strong the connection is between these two neurons. So essentially, if the weight is zero, there is no connection. And if this weight is very big, then the connection is very, very strong. In particular here, when you see the cycle here and you see the label discriminant, what we are going to do in practice on the artificial neuron is that we are going to take the input x1 and we are going to multiply it by the weight w1. And if we have more than one input, which is the case in this figure, we are going to take every single input and multiply it by its corresponding weight. And then we are going to do the sum of all of it. So when you see the discriminant and you see the label sum on the circle, essentially what we mean here is that this sum is going to be equal to x1 times w1 plus x2 times w2 plus so on and so on until we get to xn times wn. So this is what we mean by sum here. And then essentially on top of the sum, we are going to apply a function. Before we can apply the function, of course, we subtract a bias from the sum. The bias is essentially a number that is assigned to the neuron, to the artificial neuron. And essentially what we do is that we take the sum minus the bias and we apply a function on top of it. The function is usually called an activation function, and it can be of any shape. So it could be a rectifier linear unit, it could be a sinusoidal function, it can be anything. And this is going to be at the very end the output of the artificial neuron. So now that we know what an artificial neuron is, and now that we know how to connect them, in practice, we know how to create neural networks. And here on the screen, I'm reporting one plot to give you a concrete idea of what a neural network would be. And we are even going to implement this exact neural network that you see here on the screen in BASIC. So what does this plot represent here? Essentially, you have three layers of neurons, as you can see. One layer is made of green neurons. So now neurons are represented by these circles that you see here. And then we have the hidden layer, which is represented by these blue neurons. And then we have an output layer, which is represented by the red neuron that you see on the screen here. In practice, you also see the connections between these layers. So for example, if we take the first neuron in the input layer, let's say the top neuron that you see here, this one is connected with three different neurons that are in the hidden layer. And essentially you can see what connection we have through the arrows that you see here. So for example, in this particular case, the top green neuron that is in the input layer is connected to the first three top neurons that you have in the hidden layer. If you take the bottom input neuron, you can see that is connected to the first three bottom hidden neurons that we have in the hidden layer. In the very same way, you understand how connection works between the hidden layer and the output layer. So essentially, every single neuron that is in the hidden layer is going to have one connection with the output layer. So the output neuron that we have here in red is going to have 4 inputs, and these 4 inputs will come from the output of the 4 neurons that we have in the hidden layer. So this is exactly what we are going to implement in BASIC, but before we can implement this, we have to introduce more information. So I'm going to show a different plot now. In this plot, it is clear that there is way more information. This is actually the information that we are going to use to implement the BASIC program to compute the inference of the neural network. So the first labels that you see here in the input layer are I1 and I2. So these will be two variables in BASIC, and they will represent essentially the input that is provided to the network that we have here at hand. So I1 will be the input to the top neuron that you find in the input layer, and I2 will be the input that you provide to the bottom green neuron that is in the input layer. Then, as you can see, there are new labels, different labels like W1, W2, and so on until W10. This will be an array in BASIC, and this array will have an index, of course, that ranges between 1 and 10. This array will represent the array of weights that we have in the network. Both weights and biases, which are these labels that you find here, B1, B2, so on until B5, we will consider all these variables as pre-computed variables. So in the BASIC program, we will always take for granted that these values are already computed. We are going to do a few examples in the BASIC program. You will see how the weights and the biases actually affect the functioning of the neural network. So essentially, as you can see here, we will have two arrays. The first one representing the weights of the neural network. Then we will have the second array, which will represent the biases of the neurons. So these will be B1, B2 until B5. And eventually we will have a few variables, I1 and I2, which describe the input of the network, and we will have one output variable which will be the output of the neuron that you see in the output layer, so the red neuron that you find here. So this is more or less the network that we are going to in practice implement in basic. Of course, we need to spend a few words on training artificial neural networks. This would be a very long topic, which would require at least several videos to be explained. So what I will do here is I'm going to refer you to two different libraries that you can use to train your neural network, and they don't actually require a lot of knowledge in machine learning to use those libraries. The very first one is called FANN. This is a library that is written in C, but it's also compatible with Python, so you can actually use it under Python if you want to. But I would recommend it to use it in C, because if you do it, then you will immediately understand how to extract the weights and the biases of a network which has been already trained. This library is also very important, very interesting, because it includes a lot of training method, or let's say a lot of different training methods. For example, you'll be able to find gradient descent, but you also be able to find Adam. In this library here, this is another library that is written in C, and it implements many different ways to train a neural network. Again, this is a library that is very easy to understand, and if you train a neural network using this library, you will understand almost immediately how to extract the weights and the biases that you would like to use for your neural network. In this last case, if you decide to use this package to train your neural network, you might even have the chance to contact me and to ask directly questions, because this is a library that I have created myself in the past. And now we can finally focus on the example implemented on the ATARI. So the very first thing that I'm going to show is to print the listing, so that you can stop the screen whenever you need and you can go through the listing and see every single thing. But I'm also going to explain a few, let's say, lines of this listing. And actually, we are going to start from lines 1 until 90. And what do we see here? So the first two lines that are here, 10 and 12, the first line, well, it is a comment. This is the network input. And the second line here, line 12, define the input. So as you can see, we have the variable I1 and we have the variable I2. Values are assigned to these two variables, which are non-zero. So I1 has 0.1 and I2 has a value equal to 0.9. Then from line 20, we start to have a few declarations. So on line 22, the very first thing that we do here, we define the number of weights, which is in this case represented by the variable NW equal to 10. And we define the total number of neurons in the network, so excluding the input neurons. So in this case, this is represented by the variable mn, which is equal to 5. Now that we have the number of weights and the number of neurons, essentially we can define arrays. So the very first arrays that we want to define are the arrays for the weight and the bias, which are the arrays W and B. And then we want to define a few arrays for the discriminant. So this is the array D, and the array for the output of every neuron, which is going to be represented by the array O. Finally, starting from line 40, we do a few initializations. So there are a few initial conditions for the weights and the biases. And in this particular case, what we are doing is we are assigning every single weight equal to 0 and every single bias equal to 0. For now, this is what we are going to use. This is the equivalent, of course, of having an artificial neural network that has no connection between the neurons. We are going to change this later on. We are going to see what impact it has on the inference of the neural network. So we can now proceed with a second part of the code, and we are going to list lines from 100 to 142. And what you see here is essentially the inference of the neural network that has been implemented here. So the very first thing that we do here is we define the discriminants of the various neural network that, or let's say the various neurons that we have in the neural network. So if you follow the graph representing the neural network, you will see that all these formulas here are very simple. So essentially, this is the discriminant of the first neuron in the hidden layer. So this would be W1 times the input of the first input neuron. In the same way, here you have the second neuron in the hidden layer, which now has two connections. One is with the, let's say, with the top input neuron, and the second one is with the bottom input neuron. In the very same way, here we compute the discriminant for the third neuron, and finally we compute the discriminant for the fourth neuron. So these four neurons that we have here, these are neurons that belong to the hidden layer. So what we have done here is to compute the discriminant of every single neuron that belongs to the hidden layer. In the very same way here, we now can compute the output of the hidden layer. So because we have now the discriminants for every neuron. So the way we do this, as you can see here on line 124, is that first of all, we add the bias to the discriminant. So of course you can add it or subtract it. It really doesn't change a lot of things. It just depends on how you fix the signs here and how you train your neural network. But once all of this is fixed, essentially you can use whatever number you want. And now what you can see is that we take the discriminant, we add the bias, and we apply a function on top of this new number. In this particular case, the function that we apply is the sinus, the sinusoidal function. So practically the sine function is the activation function that we use here in this particular neural network. We are using the sine function. It could be actually any kind of function that we need depending on what problem one has at hand. And then in the very same way, we can compute the discriminant and the output of the only neuron that we have in the output layer. So the discriminant here, as you can see, it's computed from line 132 until line 138. And the way it is done is that this is going to be the sum of several values. Actually, there is a mistake here, so we should add the previous value of D5, and then this is going to be added to this multiplication here. And now that we have that, we can at the end compute the output of the neural network, which is going to be essentially the sine function that is applied over D5 plus B5. So this is not different from what we have done in the hidden layer, but it's just applied to the only output neuron that we have in the output layer. So that being done, we can now show the final part of the code that ranges from 150 to line 152. And what you see here is that at the very end, once all of this has been computed, what we want to do is to show the input of the neural network and the output that we have obtained from the neural network. Now that we have gone through the code, we can do a few numerical experiments. So before we do this, I want to show again the initial part of this program here. And in particular, I want to show line 12, where we define the input of the neural network. So if we run this neural network, you will see that pretty much nothing happens. And that's because on line 50, we assign every single weight being equal to 0. And then on line 80, we assign every single bias equal to 0. So if we run this, you will see that the output of the neural network is 0. But if we try, for example, to change the values of these numbers, let's say that now the input is 0, 5 and 0, 2. If I run this new version of the code, what I get is that even if the input has drastically changed, the output is still 0. Again, this is because all weights are set to 0. So it means that in practice, there is no connection between the neurons. So we are now going to do something slightly different. We still show again the initial part of the code, and this time we are going to change line 80. We are going to assign now a non-zero value to the biases. So let's say that now this value is 0.5. If you think in terms of the last neuron in the network, which is the output neuron, in the output layer, you can think of this as the sign function that is applied on the discriminant plus the bias. Now the discriminant is going to be equal to 0 because every single weight are equal to 0. But the sinus of the discriminant plus the bias is going to be different than 0 because the bias now is different than 0. As a matter of fact, if I try to run this program now, this is the output that I'm going to get. And as you can see, the output is definitely different than 0. In the very same way, we can decide to change line 50, and we can decide to assign, let's say, some value to the weight. Let's say that all the weights now are equal to 0.1. So if I show you again the initial part of the code, you can see that now things are slightly different. If we run this code, the output is going to be again different because now we have connection between the neurons. So let's try to run it. And as you can see, the value is different from the previous value. So of course, weights and biases should be pre-computed. What I am showing here is just an example on how things would work on the ATARI. The way you pre-compute weights and biases is by defining an architecture of a neural network, defining a data set, and eventually training the neural network by using some library such as FANN or neural networks. So this is something that you always have to bear in mind, but once the neural network is trained, you can load the weights and biases on the ATARI, and essentially you can run this program to have a proper inference of a neural network. This concludes the video for today. As always, thank you so much for being here, and see you in the next one.